Hello everyone, my name is Tigo. This video is made to introduce my research. Constructing an accurate and complete as-built beam based on an as-design beam and progressive laser scans. Before we get started, let us first think about why as-built beam. In this comic, the ninja tried to get to the target place following the beam file he stored. However, the beam doesn't match to the as-built condition of the building, so the ninja end up dumped into an alley. Change happens during the construction or renovation all the time. So it is important to keep the captured building information matched to the as-built condition, of course, not to help the ninja, but to help owners or facility management team to better manage and maintain buildings. As a part of construction projects, contractors are required to hand over as-built documents to owners or FM teams at the end of the project. In the current practice, as-built documents are usually made in the paper-based format, which is hard to manage and update. It is a challenging, time and cost-consuming process to keep as-built documents accurate and complete. According to a report published by National Institute of Standards and Technology, $4.8 billion were spent every year just to verify that the captured building information is accurate and up to date. As a digital representation to store building information model can be used as an information repository to capture and store the as-built information. It is easier to update and share information among different parties using BIM. However, because of construction changes or design errors, a beam created in the design phase is not equal to the as-built beam. There is a need to capture the actual building condition, based on which to remove the discrepancies between the as-designed beam and the as-built condition. Laser scanning technology is able to capture the geometric information in a timely manner. Hence, point cloud data captured by an as-designed beam can be used as the reference to update an as-designed beam into an as-built beam. However, since point cloud data is just a collection of 3D points without any semantic information, it is difficult to extract the building components and their associated geometric information directly from point clouds. By mapping point clouds with BIM, the semantic information contained in the beam can be linked to the point clouds. In this section, I will briefly talk about the motivating case study, in which I updated the as-designed beam of a newly renovation research lab into the as-built beam based on point cloud data. The process of updating an as-designed beam can be divided into 4 steps. The first step is to segment the point cloud into segmentations. In the second step, we map the segments of a point cloud to the components modeled in a beam. Due to discrepancies between the as-designed beam and the actual building condition, the mappings between the beam and the point cloud are not exactly one-to-one mappings. After the segments of a point cloud are mapped to components modeled in a beam, the next step is to compare these two data sources and identify the discrepancies. Finally, in the updating process, the as-designed beam will be updated. The discrepancies will then be removed from the as-designed beam. According to the motivating case study, I have identified 3 challenges. The first challenge is to map segments of a point cloud to components modeled in the beam, especially when discrepancies existed between the 2 data sources. The mapping between a point cloud and a beam can be achieved by reasoning with their correspondences. The correspondences can be identified based on different features, such as the shape similarity, the spatial proximity, and so on. Because of the discrepancies between the 2 data sources, the mapping identified using one type of features might be incorrect. In the right figure, the air duct fitting highlighted in the red box is not constructed as the beam specifies. If we conduct mapping based on the shape similarity, this mapping cannot be identified. The left figure is a 2D ground view of the registered point cloud and beam. The segment of the point cloud is overlapped with 2 components in the beam. Hence, additional analysis is needed in order to identify which component in the beam B1 or B2 or both should be mapped to the segment in the point cloud. Second, a component might have multiple forms during the construction or renovation phase, which further challenges the mapping process. As shown in this figure, a concrete column on a construction site starts with a rebar cage, then is surrounded by formwork, then is transformed to a solid column when concrete is poured. It is possible that the laser scans capture the column at different percentage of completion and different forms. Whereas a concrete column is usually shown in its final form in 100 completion in a beam. So it is a challenge to map segments from a point cloud to the component in a beam when the component has different forms of appearance in the two data sources. Third, laser scans performed at a single point in time only capture a partial view of a building due to occlusions or construction progress. It highlights the opportunity of progressive scanning a job site, and use the point clouds captured by the progressive laser scans in order to get a complete view of a facility. In order to address these challenges, the ultimate vision of this research is to develop a framework that supports the updating of an as-designed beam frequently throughout the construction or renovation phase with the help of progressive laser scans. As shown in the vision diagram, the job site is progressively scanned during the renovation or construction process. When a point cloud is captured, it will be mapped to and compared with the as-designed beam. After the discrepancies between two data sources are identified, the as-designed beam will be updated to remove such discrepancies. When the new point cloud is captured, we will repeat the same process again, but this time, the geometric information for the same building component captured by the two scans will be leveraged and fused together in order to improve the accuracy and completeness of the updated beam. Finally, the as-designed beam is converted into an accurate and complete as-built beam, which can be delivered to the owners as a part of the information handover documents. In this research, we will mainly focus on two parts that are highlighted in the red box in order to build the foundation for this framework. The first part is to identify and evaluate the performance of features for identifying mapping between a segmented point cloud and a beam. The second part is to evaluate the value of using progressive laser scans to improve the accuracy and completeness of an as-built beam.